Welcome. This video is about solving problems involving charged particles moving in a circle. You can find the pictures in this presentation on one of the pages in your packet with the title, Charged Particles Moving in a Circle. Pause this video if you need time to find that page. Here is a picture of a negative charge moving in a clockwise direction around a circle in a magnetic field that is directed into the page. We know that the magnetic field is directed into the page because the magnetic field is symbolized by X's, which mean are the back of the arrow, and it means into the page. You will notice first that the forces are completely perpendicular to the velocity, which is true of magnetic forces. Remember from circular motion that the acceleration when you are moving in a circle is equal to v squared over r, where v is the speed and r is the radius of the circular motion. So there's the radius of the circular motion, and v is the speed. Also remember from first semester, the acceleration of any object is equal to the net force that is acting on that object divided by the mass. Okay, in this case, the net force is supplied by the magnetic force. And the magnitude of the magnetic force is equal to QVB sine theta. Now, theta is the angle between the velocity and the magnetic field. So the magnetic field is into the page, and the velocity at any point is in the plane of the page. So at every point, the velocity is perpendicular to the magnetic field. That means sine of theta, or theta, is 90 degrees. And sine of theta, sine of 90 degrees, is just 1. So for our purposes, the magnetic force can just be written as QVB. So therefore, we can write that the acceleration, if I take this equation, the acceleration, which is v squared over r, is equal to the net force, in this case, the magnetic force, QVB, divided by m, where m is the mass of the particle. Let's write that up here. M is the mass of the particle. I can simplify this if I want to, and I will do that on the next slide to solve for the radius of the motion. So what I want to do now is to solve for the radius of the motion in terms of the other quantities. First thing that you'll notice that you can do is cancel one of the v's. So divide both sides by v, and you're left with v over r is equal to qb over m. So now to solve for the radius, I'm going to multiply both sides by r, and that cancels this r, and I end up with v equals qb r over m. Then I need to multiply m on both sides and divide QB on both sides. And what I'm left with is that mass times velocity over charge times magnetic field is equal to the radius of the motion. Now turn your page over to the circular motion and magnetic fields worksheet. Pause this video if you need time to get to that page. First, let's review the relevant equations. The magnetic force is equal to QVB sine theta. The acceleration moving in a circle is equal to v squared over r. And the acceleration of an object is equal to the net force divided by the mass. Some other equations that might be useful to you are that the velocity of something moving in a circle is the circumference, 2 pi r, divided by the time. In other words, t is the period of the motion. Also, the frequency is equal to 1 over the period. So f is the frequency. So to review from last semester, the period is the time for one revolution, one time around the circle, and the frequency is the number of revolutions per second. So the period is in units of seconds, and the frequency is in units of hertz or cycles per second. And then the equation that we derived on the last slide is that for circular motion of a particle in a magnetic field, you have that the radius is the mass times the velocity divided by the charge times the magnetic field. So those are the relevant equations for this particular practice worksheet. Most of the practice problems on this worksheet I'm going to let you do on your own, and then you can look up my answers online. But I decided that we should work problem number 3 together, which I believe is on the top of the next page, because it involves alpha particles, which are helium nuclei. So alpha particles are emitted from a radioactive source at a speed of 1.6 times 10 to the 7th meters per second. The question asks what magnetic field strength is necessary to bend these into a circular path of radius 0.25 meters. So let's write down some of our knowns and unknowns. First of all, we know that the speed is 1.6 times 10 to the 7th meters per second. We know that the radius is 0.25 meters. And we know that these are alpha particles. So alpha particles are helium nuclei. And helium nuclei have 2 protons and 2 neutrons. What that means in this case is that the charge is twice the charge on the proton. The neutrons have no charge, but the protons have a positive 1.6 times 10 to the negative 19th coulombs. So the charge on the helium nucleus is 2 times 1.6 times 10 to the negative 19th coulombs. And so the charge on an alpha particle is 3.2 times 10 to the negative 16th. Sorry, negative 19th. Let me erase that real quick. Negative 19th coulombs. And the helium nucleus is 2 protons and 2 neutrons. Now the mass of the neutron we're going to say is almost exactly the same as the mass of a proton. So we can essentially say that the mass is 2 times the mass of the proton plus 2 times the mass of the neutron. And we're going to say that those are basically the same. So we're going to say that that's practically 4 times the mass of the proton. So the mass of the helium nucleus, or the alpha particle, is 4 times the mass of the proton, which is 1.67 times 10 to the negative 27th kilograms. If you don't have that memorized, then please feel free to look it up on your pink equation sheet. When you multiply that out on your calculator, what you get is 6.68 times 10 to the negative 27th kilograms. So 6.68 times 10 to the negative 27th kilograms. So those are all of our knowns, and what we're looking for in this case is what is the magnetic field strength. So B equals question mark. So remember, you're going in a circle, V squared over R, and it's caused by the magnetic force, QVB over, and then so the magnetic force divided by the mass. So this is basically the acceleration here is equal to the mass, or sorry, the force divided by the mass. And once again, we can cancel one of the V's, and we're left with V over R equals QB over M. And I want to solve this for magnetic field. So I want to isolate the B, which means I multiply both sides by mass. So that's mass over mass is 1. And I divide both sides by Q. So Q over Q is 1. So mass times velocity over charge times radius is equal to the magnetic field. So I'm going to change colors when I plug this in. I'll do this in red maybe. Magnetic field is equal to mass. We said that was 6.68 times 10 to the negative 27th kilograms, times the velocity, which was 1.6 times 10 to the 7th meters per second, divided by Q, which was 3.2 times 10 to the negative 19th coulombs, times the radius, 0.25 meters. So plugging this all into our calculator, we end up with a magnetic field that is 1.336 Tesla. So there you have it. The equations, the concepts, and a practice problem on charged particles moving in a circle. Good luck with your worksheet.